All right, so in this video, we're going to be looking at how to find the equation of a plane in 3 dimensions from different starting descriptions. Now, we saw in another video that the basic way that you find the equation of a plane is you start with a vector that is normal to the plane and a point on the plane. And you end up with an equation that looks like so, where ABC is the vector perpendicular to the plane, and x naught, y naught, z naught is the point on the plane. But you're not always given that information directly. So frequently you're given information indirectly. And so you have to use that information, manipulate it a little bit in order to get to particularly the normal to the plane, the vector that is normal to the plane. So I want to go through a couple of examples and just think about the steps that you need in order to get to that normal to the plane. Now, probably the longest version of this process is to start with a point. So if you start with a single value or 3 points in the plane, then you can work your way up to that normal equation. So starting from 3 points. So let's say I have the point 3, -1, 2, and I have the point 8, 2, 4, and I have another point -1, -2, -3. So in order to get to the normal equation, I'm going to need vectors in the plane. So I'm going to label these A, B, C, and I'm going to come up with 2 vectors between those points. So let's say A, B. Let's say the difference between these 2 points. So 8 minus 3 is 5, and 2 minus a -1 is 3, and 4 minus 2 is 2. And then let's say BC. And again, the order you do the subtraction, it doesn't matter for this context. We just need 2 vectors in the plane. So converting our points to vectors. So let's say BC, so -1 minus 8 would be -9, and -2 minus 2 would be -4, and -3 minus 4 would be -7. So then, in order to get the vector which is perpendicular to the plane, then you would need to do the cross product. So AB cross BC. Got our I, J, K, and our 5, 3, 2, and our -9, -4, -7. And then we end up with, so in the I component, we're going to end up with -21 plus 8. And then in the J component, we have another negative, and it's going to be -20 plus 27. And then in the K component, nope, that was not the J component. That was 5 times -7 is -35. And then -9 times 2 is -8, is +18. I was doing the K component. And then in the K component, we have -20 plus 27. And if we simplify that, we're going to end up with negative 21 plus 8 is going to be negative 13. And negative 35 plus 18 is going to be negative 17, but then there's another negative. And then negative 20 plus 27 is going to give me 7. And so from here, I can take that vector or is trying to be helpful and it's not being helpful. From here, I can take that vector and any of the 3 points that I was originally given and then create my equation of the plane. So negative 13 x, let's say just take the first one, minus 3, minus 1, just to be explicit. Sorry, plus 17, I'm doing it again, y plus 1, and then from the vector plus 7, z minus 2 equals 0. Yes, try not to get the points and the vectors confused. So that would be, again, you can simplify from there, but that would be my equation of the plane. Now, this is the longest process. When you start from 2 points and you work your way up, you have to find the vectors, and then you have to do the cross product for the vectors, and then finally you can put things into the equation of the plane. Now, most of the other ways that you're going to get information about the equation of the plane are not going to be this long, but you might get vectors that are in the plane, so you might need to still do the cross product, or you might get information more indirectly. So let's look at a couple other examples, because every example is going to be just a little bit different. So, and another example might be find the equation of the plane that passes through the point -1 to 1 and contains the line intersection of the planes x plus y minus z equals 2 and 2x minus y plus 3z equals 1. So the line of intersection between these planes is in the given plane. So what I know is that I need to find the equation of the line of intersection, because that's going to be a vector that is in the plane. So my 2 vectors, normally when you have an equation like this, what you're going to do is you're going to basically do substitution and come up with the vector for the line that way. So if I take my first equation and I solve it for z, I'm going to get x plus y minus 2 is equal to z. And then I'm going to plug that into my other equation, 2x minus y plus 3 times x plus y minus 2 is equal to 1. And then if I simplify, I get 5x and my plus 2y and I move the 6 over, I get 7. And then I can let one of these parameters be equal to t to get the vector. So if I say x is equal to t, then 5t plus 2y is equal to 7. And so 2y is equal to 7 minus 5t, and y is equal to 7 over 2 minus 5 over 2t. And then I can plug both of those into the z equation. Z was equal to, so x was t, and y was 7 over 2 minus 5 over 2t minus 2. And then if I simplify, I'm going to get minus 3/2 t and 7/2 is 3.5 minus 2 is 1.5, so 3/2. So my equation of the line is going to be t 7/2 minus 5/2 t and minus 3/2 t plus 3 over 2. And so the vector for that, the direction vector, is going to be 1, negative 5/2, and 3/2. So that's a vector that is in the plane. And I also need another vector that is in the plane. What I can do is I have a point in the plane already, and so I can find another vector from 2 points in the plane. And so what I'm going to do is I'm going to take the point that was in the plane and the point that I have that's going, this one of the points that goes through this line, for example, 0, 7/2, 3/2. That's when this line is 0. That is a point that goes through the plane, goes through this line, and therefore is in the plane because the line is in the plane. And I had before, I had my point earlier was -1, 2, 1. So now I have to just come up with a vector, we'll call it v, which is also in the plane. So maybe between these 2 points. So -1 minus 0 is -1. 2 minus 7/2 is going to be minus 3/2. And 1 minus 3/2 is going to be minus 1/2. And if I want to, for both of these vectors, particularly when I put them in my cross product, I can rescale them just so that I don't have to deal with fractions and everything. So rescaling them will not affect the direction or anything like that. So what I'm going to do is I'm going to do 2u cross 2v just so that I can get rid of those fractions. I, j, k. Now, if I multiply this vector by 2, I'm going to get 2 minus 5, 3. And if I multiply this vector by 2, I'm going to get -2, -3, and -1. Now we do our cross products. For the I component, I have 5 plus 9. And for the J component, -2 minus, no, plus 6. And then for the K component, I have -6 and -10. And so I'm going to end up with 14, and -2 and +6 is going to be 4. And so that's -4 and then -16. And so then now my equation of the plane, I can use the original point they gave us, and 14x plus 1 minus 4 y minus 2 minus 16 z minus 1 equals 0. Now, sometimes they'll give you information about something that is perpendicular to the plane already. So consider you have a plane passing through -0, -2, 5, and -1, 3, 1, and is perpendicular to the plane 2z is equal to 5x plus 4y. Now, the thing to keep in mind about if you're perpendicular to this plane, then that means that the vector that defines this plane is parallel to your plane. It's not, again, vectors can be moved around because they don't have starting points. So it might not be in the plane, but you can think of it as a vector that is defining a direction of the plane. So you can think of it as being in the plane. So what we're going to do is we're going to first rearrange this equation. 5x plus 4y minus 2z equals 0. So our vector in the plane is going to be 5, 4, -2. And then we can get, since we have 2 points, we can get another vector in the plane by getting a vector between these 2 points. So -1 minus 0 is -1, 3 minus -2 is 5, and 1 minus 5 is going to be -4. And then we can do the cross product for these vectors in order to get our vector, which is perpendicular. I, J, K. And so 5, 4, -2, -1, 5, -4. The I component is going to be -16 plus 10. The J component is going to be -20 minus 2. And the K component, 25 minus plus 4. -6 and 22, and 29. And so we'll have negative 6x, and then we can use the original, one of the original points, either one is fine. Plus 22y plus 2, and then plus 29 z minus 5. Now, the other thing to kind of keep in mind, the order that you do the cross product in could change the signs, so you could get different signs for these problems. That's totally fine. That doesn't change anything. And again, if you use a different point, this stage will look a little different, but if you simplify, you should get the same equation. Now, sometimes they'll be nice to you and they'll give you another plane that the plane is parallel to. So, for example, the plane passes through the point 3, 5, minus 2 and is parallel to the plane x minus 2y plus 4z equals 11. Now, if they are nice enough to do that, well, then you don't have to do any of the cross products or things, because if two planes are parallel, they have the same normal vector. And so the vector that you need is just the coefficient of the vector of the plane you already have. So 1, -2, 4. And so you just insert the points that they've given you, x minus 3, minus 2, y minus 5, and 4, z plus 2. And so the only thing that is going to change eventually when you simplify this is going to be this constant on the end. Now, again, that's the easy version. As we've seen, most of the time, they're going to give you information that is less direct. And then you're going to have to come up with more information and then do a cross product in order to get there. Now I'm going to describe a couple other scenarios. We're not going to go through absolutely all of them because there's so many possibilities. So some alternatives that you might encounter. Again, we've seen examples where we have intersection of planes. You could have given lines in the plane. Now, if you have lines in the plane, then the direction vectors are parallel to the plane. And so you can do the cross product to get the normal vector. You could be given vectors that are directions in terms of angles. So sometimes you'll get information like a vector in the plane makes a 30-degree angle with the y-axis, for example. So recall that, again, depending on the coordinates that you're using, you can create a direction vector from sines and cosines. A vector like this would be in the xy plane, so it would be an angle between the x and the y axes. But in the xy plane, if you move these coordinates around, then you can get them in the yz plane, or you can get them in the xz plane. And so then you can come up with vectors that give you directions in those planes. If those are part of your inputs, then again, you can always rescale them to get rid of any denominators or whatever to make them nice whole numbers. But this is another way that you might be given direction vectors that are in the plane, or even potentially perpendicular to the plane. So there's a whole bunch of different ways that they can give you this information. And so the thing to keep in mind is you always have to be able to extract vector information if it's already perpendicular to your plane, like it's already a normal vector as in this last one, you don't have to do any cross product. But if it's going to be information that is not perpendicular, but is somehow in the plane or parallel to the plane, then you're going to need to be able to do that, find those vectors. You need two of them to do the cross product. That will get you your normal vector to the plane, and then combine it with any point that's on the plane. And then that will give you your equation.